Our star, the Sun, and its significance. The Sun, a blazing ball of plasma that dominates our sky. This celestial giant is the center of our solar system. It holds everything together with its immense gravity. Without the Sun, there would be no life on Earth. It provides us with light, warmth, and energy. Understanding the Sun is crucial for understanding our place in the universe. The Sun is a star, one of billions in the Milky Way Galaxy. It's a giant ball of hot gas, mostly hydrogen and helium. The Sun is constantly churning and changing. These changes can have a profound impact on our planet. Scientists have been studying the Sun for centuries. They use telescopes and spacecraft to observe it. We are constantly learning more about this complex and fascinating star. The Sun is a source of endless wonder and discovery. Journey to the center of the Sun, unveiling its structure. Let's imagine a journey to the heart of the Sun. We begin at the core. This is the Sun's innermost region. Temperatures here reach a staggering 27 million degrees Fahrenheit. This intense heat is where nuclear fusion occurs. Hydrogen atoms smash together, forming helium and releasing enormous amounts of energy. Moving outward, we encounter the radiative zone. This dense region is where energy from the core slowly travels outward in the form of photons. These photons can take hundreds of thousands of years to escape. Next, we reach the convective zone. Here, the Sun's material is in constant motion. Hot plasma rises while cooler plasma sinks. This creates a churning effect. Finally, we arrive at the Sun's visible surface, the photosphere. This is the layer we see from Earth. It's a thin layer, only about 300 miles thick, but it's where we observe many of the Sun's most fascinating features. Beyond the photosphere lie the chromosphere and the corona, the Sun's outer atmosphere. The photosphere, a glowing sea of plasma. The photosphere is a sea of plasma. Plasma is a superheated state of matter. It's like a gas, but the atoms have been stripped of their electrons. This makes the plasma electrically charged. The photosphere is incredibly hot. It has a temperature of about 10,000 degrees Fahrenheit. The photosphere is not a smooth, uniform surface. It's covered in granules. These are small, bright regions. They're caused by convection. Hot plasma rises in the center of the granule. It then cools and sinks at the edges. The photosphere is also where we observe sunspots. These are darker, cooler regions on the Sun's surface. Sunspots are caused by the Sun's magnetic field. Section 4. Sunspots. Dark mysteries on the solar surface. Sunspots appear dark because they are cooler than the surrounding photosphere. But don't let their darkness fool you. They are still incredibly hot. Sunspots can be thousands of degrees cooler than the surrounding photosphere. Sunspots are not permanent features. They come and go in a cycle. The number of sunspots on the Sun's surface varies over an 11-year period. This is known as the solar cycle. At the peak of the solar cycle, there are many sunspots. At the minimum, there are very few. Sunspots are closely linked to the Sun's magnetic field. They form in regions where the magnetic field is particularly strong. These strong magnetic fields inhibit the flow of heat from the Sun's interior. This creates the cooler regions that we see as sunspots. Section 5. Magnetic dance, the Sun's dynamic magnetic field. The Sun's magnetic field is complex and constantly changing. It's generated deep within the Sun, in the convective zone. The movement of plasma in the convective zone creates electric currents. These electric currents, in turn, generate magnetic fields. The Sun's magnetic field is not uniform. It's strongest at the poles and weakest at the equator. The magnetic field lines also get twisted and tangled due to the Sun's rotation. This creates regions of intense magnetic activity. One of the most dramatic manifestations of the Sun's magnetic field is magnetic reconnection. This occurs when magnetic field lines break apart and reconnect in a different configuration. This process releases tremendous amounts of energy. Magnetic reconnection is responsible for many of the Sun's most explosive events, such as solar flares and coronal mass ejections.